It's like my heart beating a little fast, yeah. Yeah, because I've been looking forward to this. It looks fun.
Did you get copyrighted?
Yeah, well, sort of. I mean, the button I need to press, muted stuff, and whatever. I'm still in trouble. Hey, listen. Not in this class, but in the other class, I think it was yesterday, somebody said, oh my gosh, Mrs. Ward, what are we doing all this for, blah, 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 blah. So I just grabbed a handy calculus textbook, and I opened it up, and page 1 right there. These are the derivatives and integrals that you'll learn about in calculus class. But on the very next page, a whole page of trigonometry, including all of the identities we talked about. Reciprocal, quotient, Pythagorean, cofunction, even, odd, all that. You gotta know it, okay? Some of you say, I never use this in my real life. You may not. But you're all going to take calculus and you're going to use it in calculus class, right? So, there you go. So, no whining and complaining. We're going to forge ahead and we're going to get smart. All right, let's get our notes out. We're going to pick up where we left off. Oh, well, that's on video. All right, so here we go. I think we're on page 59. And it looks like we are ready for letter E. So remember, our job is to change one side into the other. So, as I am writing this down, hopefully you are thinking about what you might do. There is no one way to start. I started made on this one. But I need you guys to focus, stop talking, unless you're talking about this. What is our strategy going to be? How do you want to start? Alana, I see your hand up back there. What do you think?
Can we start by taking the greatest common factor out of parentheses?
Oh. Alana says, when I look over here, I can actually take something out of that parentheses. So I'm going to go ahead and pull out a sine squared, right, Alana? And I would have 1 minus 2 sine squared plus sine to the 4th. And then I still have my cosine there on the end. All that's multiplied together. All right. That looks good. What do you see now? Seth? This right here, you guys, factors. Now, I know it's a little confusing with signs in there, but if you look at that, that is the same as 1 minus 2x squared plus x to the 4th. I mean, that's the pattern that's there. And how would this factor, if this is what you had, like in your Algebra 1 class, how would that factor? 1 minus x squared and 1 minus x squared? So how does the real thing factor? Oh, this is like extra. The real thing factors as 1 minus sine squared times 1 minus sine squared. Ding, 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 ding. There should be like fireworks going off in your head. What's 1 minus sine squared? Cosine squared. 1 minus sine squared is cosine squared because of the fundamental identity. So you have sine squared times cosine squared times cosine. Because these are both cosine squares. So what have you got here? Cosine squared, cosine all multiplied together is cosine to the fifth. And you did it. You did exactly what you were supposed to do. David?
Is there like a sheet for all of the, like, 1 minus sine 2
It's
sine
in your
squared?
notes. They're all in your notes. Now, we have to remember that in your notes, it's gonna say sine squared plus cosine squared is 1. But that can appear in different forms. You can rearrange that equation. Okay? All right. Okay, well, let's see, what else? That's so fun. Okay, let's see about this one. Now, I don't know about you, but I think I'm gonna try to do some stuff over here on this side. Charles?
Would you want to get a common denominator?
You know what? You absolutely could. You 100% could. What I'm wondering though, Charlie, is if it might, I don't know, I'm thinking it might be easier to do something with this first. Because what do I have on the bottom there? Secant squared? 1 plus, or no, that's not secant squared. 1 plus tangent squared is secant squared. So 1 minus tangent squared isn't anything. So yes, Charles, we're gonna get a common denominator. I guess, unless, you wanna change these into sines and cosines? Would that be easier to start maybe? That might be smarter because that's what I'm trying to end up with. So, getting a common denominator, 100% okay. Not a problem.
Like 1 plus tan squared equals secant squared, right?
Mm-hmm.
So if it's 1 minus tan, could you like make it like a negative secant?
No, because a negative secant squared would be -1. They would all have to be negative. You can't change a plus into a minus, unfortunately. So I'm going to go ahead. This is 2 sine over cosine over 1 minus sine squared over cosine squared. Now, again, there are lots of ways you can approach this problem. One of the problems in yesterday's notes, I did 3 different ways yesterday. The same problem, can be done lots of ways. Okay, this is a complex fraction. We want to fix it, we want to clean it up. So, in order to clean that up, the easiest thing to do is to multiply each fraction, or the top and the bottom, by the common denominator of both of those fractions. So this fraction is cosine, this one is cosine squared, so I'm going to multiply top and bottom by cosine squared. Now, that's perfectly legal. That's like multiplying by 1. I don't need to do it to this one because this is a whole separate fraction. I'm simplifying this. Now, what's going to happen on the top? Well, he's going to cancel with one of these. So I'm going to be left with 2 sine cosine on the top. Now, what's going to be on the bottom? Not 1 minus sine squared, cosine squared minus sine squared. Because I have to multiply the 1 by the cosine squared also. And then that will cancel with that when I do that. thought, pre-thought, will save us a little bit of effort later on. These denominators need to match. So, boy, making them match by multiplying them together, that's going to be a pretty big denominator, and it's going to be pretty messy on top too. So what I want you to think about is this. What if I thought about that second denominator as cosine squared plus cosine squared minus 1? Now, it is that, right? What's this? Remember, sine squared plus cosine squared is 1. So what's what's cosine squared minus 1? Rearrange that equation. What will it equal? Negative sine squared. Cosine squared minus 1 will equal negative sine squared, won't it? So look what happens, kids. If you substitute that in for that circled thing, what do you notice about your denominators? They're the same? Now, that's one of those things that a brand new identity verifier might not pick up on, but remember, when you have squared functions, you should always be thinking about those identities. I was thinking about it here, but it didn't work. They don't always work. But think about taking advantage of those. So now I have my common denominator, so I have 2 sine cosine plus 1 over cosine squared minus sine squared. Now, this is where you're going. Are we anywhere near that? Do you see anything at all? What? The denominator factors? How does the denominator factor? Cosine plus sine and cosine minus sine? Why does the denominator factor that way? What do we have here?
Difference of squares.
The difference of squares. The difference of squares on the bottom. Now wait a second. This is, you're going to have to really get tricky. In order to end up with what I want to end up with, don't I have to cancel something out? Doesn't this have to cancel? If I want to end up with just that in the denominator? So who's got an idea how we might make that happen? This is going to take a little bit of trickiness. And I'll give you a hint. The clue is already on the board. The clue has already been written on the board. What does 1 equal? What does this 1 right here equal? Sine squared plus cosine squared? So I can write my numerator as sine squared plus 2 sine cosine plus cosine squared over my denominator. So I changed this 1. Now there are many things I could change 1 into. change it into tan times cotan. I could change it into secant times cosine. But I changed it into this so that I had my sines and cosines up there. Now what do you notice about that numerator? It's what? It factors. It's a perfect square binomial or trinomial. This thing factors. How does this thing factor? Sine plus cosine, sine plus cosine. This is the same as x squared plus 2xy plus y squared. So it factors as sine plus cosine times sine plus cosine. Now I know what some of you are thinking, oh my gosh, I can't do this. Stop thinking that, because you can, but it is going to take some practice and it is going to take some real thinking. If you FOIL this out, some of you are still looking up here quizzically, if you FOIL this out, don't you get this? Doesn't this multiply together, give me this? So what happens? And what am I left with? Exactly what I wanted, yep. Now, I would say, for purposes of this class, on a scale of 1 to 10, I would say that's probably a 9. It's one of the tougher ones. That's a tougher one.
It's up there.
So like to that, you might want to put that on another sheet of paper, run through it again on your own. What were some techniques we learned? You'll probably never see that particular problem again, but what are some of the techniques we learned? David? Yeah, you can, if you have a 1 that you don't want, are there any 1s in this problem? Any answer here? No. So how do you get rid of a 1? Well, you could add it to a -1 if you had one of those, but you can also rewrite 1 in lots of different ways. What else did we do here? We did a lot of factoring. You gotta be on the lookout for especially trinomials that factor, or somewhere I had the difference of squares. Binomials that factor. All right, let's see what's next. Oh, we've done one like this. Can you remember, we had one that looked like this yesterday. Anybody remember what we did with that yesterday? Yeah, lots of things you can do with it, but do you remember what we did yesterday? Well, we looked at it and said, okay, let's say you're going to work from here to here. Okay, so let's say you're going to mess around with this. If that's where I'm going, right there, then I either need to put a tangent in the bottom of this, or I need to put a secant plus 1 in the top. Since I put a tangent yesterday, I'm going to put a secant plus 1 on the top. Perfectly legit, guys. And I'm doing it because I need one on the top. I need that up there in the top. Now, what's on the bottom? I can distribute, FOIL it out, and I get secant squared minus 1. That just makes my heart go, because I have an identity that I tried to use before. 1 plus tangent squared is secant squared. So what is secant squared minus 1? Tangent squared. So now I have secant plus 1 times tangent cotangent squared? And what's gonna happen? Tangent's gonna cancel, and I'm gonna be left with secant plus 1 over tangent, which is exactly what I wanted to end up with.
For the secant plus 1, do you just get that because it's the inverse?
No, I get it because this is where I'm starting, this is where I'm going. I want that on the top. Okay, so on a scale of 1 to 10, that's about a 2. That one you should be able to manage without too much trouble. All right, what about this one? Well, there has to be a lot of canceling here. I'm going to give you a minute to work on this on your own. There has to be a bunch of stuff canceling out because you got to end up with just 1 over here. So see what you can make happen with that. And I'll give you a hint if you want it. You might consider changing it into sines and cosines. You might consider that. You're not gonna need this, I don't think. Okay, you got till I'm done taking attendance.
Go for it. Go get it about. Gotta get it, 'cause it's everything of everything was that. Let's go. I know I got it right, and then like the test is over. And I just have like 4 more. That's what I was doing. And then I'd be like, oh, let's bring the one back over.
Okay, what are some thoughts that you had on this? Okay, we can do that if you want to. Okay, let's just go with the suggestion point of view. So this one needs a secant, and this one's gonna need a sine. So now I'm gonna have secant, cosecant, minus cotangent, cosecant, sine, all over secant sine. Does that look okay if we decided that's how we wanted to start, was getting a common denominator?
It's like, seems like a stupid question, but like, wouldn't it not technically like be breaking any rules if I just multiply the 1 by all of that?
You mean by the denominator?
By literally everything. Like, why can't you just do that?
Okay, so tell me what you want to multiply by?
Literally, like the whole left side, I changed the 1 into that, because I multiply by everything and then. See, okay, so I get that it's like, I get that it's like a stupid way to do it.
No, I don't understand what you're saying. What is actually multiplying?
All of it.
I get what he's saying.
What is
But then you switch the
Is
same
it just
thing.
all solutions?
No,
All solutions?
when you,
Yeah.
Just like
that's a property of equality. You multiply both sides of an equation.
answer is yes or no.
We do not know that this is an equation. So So we can't use any of the techniques, any of the properties of equality can't be used, okay? So the short answer is no. All right, what about this right here, guys? What's it? We need to figure it out. What's that? Cosecant times sine. What's cosecant times sine? Cosecant and sine are reciprocals of each other. So when you multiply them, they cancel out. So that part's at least taken care of. So we still have secant, cosecant, minus cotangent, all over secant sine. Now, if your goal, which it is to get all this junk to cancel out, shouldn't we be trying to make them the same things instead of having secants and cosecants and cotangents and all this stuff, make them the same? So let's change them all into sines and cosines and see what happens. So 1 over cosine sine. This is 1 over cosine, and this is 1 over sine. So when I multiply them, I get 1 over cosine sine. Minus cosine over sine over sine over cosine. Because this is 1 over cosine times sine. Orna?
Could we have just done that at the beginning?
I would have. Yes, that would be my preference. Somebody wanted to get a common denominator, so that's okay. But yes, with this, it's okay. It doesn't matter. It's fine. But yeah, I would have done that. It's okay. Here, this is where we are. Okay. Now, we have a giant complex fraction. So we're going to multiply every piece of it by the common denominator, which is cosine sine. So everything's getting multiplied by cosine sine. You with me? Now, we did that to cancel. This goes away, and all we have left is 1. Minus, okay, this goes away, so minus cosine squared. This goes away, so the bottom is just sine squared. Exactly. Isn't the numerator sine squared? So what do we got here? Sine squared over sine squared, which is 1.
Can you repeat that?
1 minus cosine squared is sine squared. So sine squared over sine squared is 1. When the top and the bottom match. Right? This is your fundamental identity. Sine squared plus cosine squared is 1. Okay? Alright, we're going to forge ahead, but before we do, I'd like you to get out your identities packet that I gave you. Look at all these. Millions of them. Get out your identities packet.
Sine squared. 1 minus cosine squared.
How did you get one of those?
Well, then, you have to get one of those. So, let's see. Allie is leaving, so I'll let her pick one. So, Allie, let's stick with the okay? Pick any one you want, either column A or column B, I don't care. Pick one. Yeah. Worksheet 1, worksheet 2. We'll start there. Allie's gonna pick one from either worksheet, and we're gonna do it. From worksheet 1, number 11. All right, so get out a sheet of paper. Pretend that you have been handed a quiz, and it has one problem on it, and that problem is this. This is problem number 11 on worksheet 1. Okay? So gather your thoughts. First of all, the variable in this identity is theta. If you want to make that an x, it's perfectly okay. It doesn't matter what variable you use, just make sure you're using the variable. Alright, so you have been given this problem. Your job is to change one side into the other side. You are not allowed to change both. So, what do you want to do? Go ahead.
Foil.
So you're gonna start over here and he wants to foil it. Perfectly legitimate move, right? So what happens when we foil it? We get 1 minus sine squared. Okay, well, my heart's all a twitter because, by the way, I'm wearing my heart jumper today because I forgot to wear it on Valentine's Day. But it's good to do identities in my heart jumper because my heart is pitter-pattering. 1 minus sine squared is cosine squared. Now, David?
Should you change the 1?
No, because I can't look on that side. I'm stuck over here. But I do need a fraction, right? So cosine squared would be 1 over what? 1 over secant squared, absolutely. Isn't cosine the reciprocal of the secant? And I did that because I needed 1 over. So let's make it 1 over secant squared. But wait a minute, what's secant squared? 1 plus tangent squared, and there you go. You did it. Okay, now since you got a whole sheet of paper out, let's pick another one. That one was from worksheet 1. Let's pick one from worksheet 2, and we'll let a boy do it. We'll let Joseph do it. Pick one from worksheet 2, Joseph. Number 6? Okay. So worksheet 2, number 6. Oh, we've already done this one, Joseph. It was our first example. I thought it looked familiar. So pick another one.
And let's do this one. Number
19.
Well,
Oh, this is a good one to do. This is number 19 on worksheet 2. And it illustrates another kind of hint that I have for you. So, a minute ago, we did a big long problem, and it was full of all these weird random functions, so we changed everything into sines and cosines. That's always an option. So certainly, I don't know which side you want to work on, but you could change your tangents or your cotangents into sines over cosines. Would you agree? And that will work. You'll get it eventually. It's all going to come out fine. But if you want to be a little bit more efficient about it, is there a way, let's say I want to work over here. Is there a way to directly change tangents into cotangents? So without doing the intermediate step going to sines and cosines, we'll just go straight to tangent is 1 over cotangent on the top and the bottom. If you worked on the other side, you would change your cotangent into 1 over tangent. The amount of work is going to be the same, doesn't matter. Now, when you do that, you've got a complex fraction. So we're going to multiply every single piece of the fraction by cotangent. And you don't have to write this down, but I encourage you, at least in the beginning, to write it down so that you can physically see what's happening. You're going to be left with cotangent plus 1 over cotangent minus 1, which is exactly what we wanted, right? See how easy that was? How quick that was? If this had been some other function, like a cosecant or something, then I would have changed into sines and cosines, because there's no way to get them directly from 1 to the other. Okay, I would use one more. Let's go ahead and pick another one somewhere from this sheet. Any problem from this sheet? Let's see, Brooke.
Yes. We do number on worksheet 1, number 8.
Okay, now number 8, we can just talk about that on worksheet 1. It is not an identity. We're not verifying it, we're just simplifying it. So look at your numerator in number 8. What is 1 minus sine squared? Or crap, what's 1 minus cosine squared? Sine squared. So we have sine squared over sine, and that reduces to just sine. Yeah, so that's not an identity. Brooke, pick again. Pick one from 10 through 20 or the other side. 1 to 19.
On worksheet 1, 15.
15. Looks like a mess for sure. So as you are copying down 15 on your paper, this is worksheet 1, number 15. As you are copying it down, what are you thinking about doing? I hope I copied it right. It would be disastrous if I didn't. So what do you think, Joseph?
Well, if we're trying to get it to sign, and we're trying to get rid of the, tan in the bottom, I assume, then can't we change the cotangent to 1 over tangent and then that what would that be?
Well, you can always change a cotangent into 1 over tangent. Here's my question to you. You can do that. It would not be wrong. You can do that. But since I want to end up with sine, not tangent, why don't I just change everything to sine over cosine, or sine and cosine, and see what happens? Does that make sense to you? So we can do what you said, but I don't think it's going to help us. So we have 1 over cosine over sine over cosine plus cosine over sine. you need to memorize the basic identities, the reciprocals, the quotient identities. You need to get those memorized so that you can go straight from here to here without any trouble. As has happened a bunch of times today, this is a complex fraction. And so what am I going to need to multiply by? You need to multiply by the common denominator of the whole shebang. So you're going to have to multiply by sine and cosine. Not sine plus cosine, but sine times cosine. So everything's getting multiplied by sine times cosine. And you did that, why? So that you can cancel. And here we go. What's left on the top? That's good news. What's left on the bottom? Oh my gosh! So what's left on the bottom? 1. So what do we end up with? Sine over 1, which is sine, what we want. Okay? Alright, well I could do these all day, every day, but we don't have time to do that, so we're going to move ahead. However, when you have free time, and that includes when you're social media, whatever you guys do, tweet, all that junk, set it aside, do a couple of identities for practice. You got a whole sheet. And then, if there's one you can't get, maybe we can share it as a group and figure it out.
Are we gonna do any where it doesn't work?
We will eventually, but not right yet. Okay, all right, so now, okay, so 5-2 homework, 5-2 homework is gonna be due on Friday.
This is weird.
5-2 is due on Friday, that's identities. We have office hours on Friday. And we'll make time in class to do 1 or 2, not the whole sheet. So give those a shot, see what you can do. All right, now, page 60. 5.3, sum and difference identities. There are occasions, and I talked to Shadia this morning, these are important in calculus, these sum and difference identities. I mean, you're going to use them in your calculus classes. The sum and difference identities allow you to find the sum of difference of 2 angles. The sine or cosine of the sum or difference of 2 angles. Okay? So they're all right there. There are the identities. Now, I want you to notice something. Look at the sign of alpha plus beta. And again, I'm using alpha and beta because that's what they show up as in every textbook you look at. But you can use X and Y, A and B, P and Q, I don't care. The variable doesn't matter. But notice that for the sum and the difference of the sign, so the sign of alpha plus beta and the sign of alpha minus beta, notice that the 2 formulas are identical, except for the sign in the middle, right? The SIGN in the middle. So it's sine cosine plus cosine sine and sine cosine minus cosine sine. Okay, now look at the cosine identities. Are they also identical to each other? I mean, the 2 cosine formulas are identical except for the sign in the middle. Now, it helps me remember that in the sine formulas, the signs are the same. So what I mean by that is, when it's the sign of alpha plus beta, there's a plus sign in the formula. When it's the sign of alpha minus beta, there's a minus sign in the formula. So I remember that alliteration. The sine formulas, the signs are the same. Notice that in the cosine formulas, they are different. Right? The sum is a minus and the difference is a plus. Okay? And then the tangent formulas are just different. Tangent's just different. They are the same, except for their SIGNs. And I remember this tangent is sine over cosine. So the sine stuff is on the top, and those signs are the same. So the tangent of alpha plus beta starts out as tangent plus tangent. You're gonna memorize these however you memorize them. Put them on flashcards. Quizzle it. You know how to do that? I don't. But whatever works for you, that's what you want to do. Now, how do we use these identities? Well, let's look at this for a second. Up until today, the only angles that I have been able to ask you to evaluate sine or cosine for without a calculator have been 45, 60, or 30, and then the quadrantals, 0, 90, 180, 270, right? You can do those. Here's a 15. Now, 15 is not a totally random number. 15 could be considered the difference of 60 and 45. Would you agree with that? It could also be the difference of 45 and 30. And it doesn't make any difference which way you think about it. The answer will be the same. The work will be different, but the answer will be the same. So for these problems, the first thing you're going to do is look at whatever angle you've been given. In this case, it's 15. And you're going to try to write it as one of your special angles plus another or minus another. So I chose 60 minus 45. So this is a difference. It's a cosine. This is my alpha, and this is my beta. So I'm going to plug and shove. Cosine 60, cosine 45, plus sine 60, sine 45. Now, were you able to follow that from the formulas? Cosine alpha minus beta is cosine cosine plus sine sine. Now guess what you get to do. 1, 2, 3, 4 numbers need to be plugged in. So 60 looks like this. If you thought you were done with this, forget it. This follows you forever. 45 looks like this. You know what I'm doing here? Okay. So now I'm going to look at my pictures. The cosine of 60 is 1/2. The cosine of 45 is 1 over root 2, which I'll write as root 2 over 2. Will this help me later? The sine of 60 is root 3 over 2. And the sine of 45 is another root 2 over 2. Anybody have a question about that part? Now we're multiplying fractions. These two are multiplied, so that's going to be root 2 over 4. Please don't cancel anything. That's under a radical. This is not, so you can't do anything there. This one is root 6 over 4, because the square root of 3 times the square root of 2 is the square root of 6. And they do have a common denominator, so I'm just going to go ahead and add them. Now I can't combine them, they're not like terms, but I can write it as one fraction instead of 2. If you typed into your calculator cosine 15, you would get a decimal. This is called the exact answer because there's no round off. I did it by hand, there's no round off. Okay? All right, let's look at the next one. Sine 75. What do you think we might want to do first? It's sine 75.
30 plus 4.
Okay, so we can think of that as the sine of 30 plus 45. Would everybody agree with that? Remember, somehow you gotta make your angle a special angle. So 30 and 45. All right, our formula says this is your alpha and your beta. It's a sine and it's a sum. So it's sine 30 cosine 45 plus cosine 30 sine 45. You're just plugging your alpha and beta into the sine sum formula. David?
Where do you get the cos from?
Look at your formula for the sine of alpha plus beta. We're just plugging it in.
Does it matter?
Now, just like before, you've got 4 values here that you have to do. And I left my triangles up here because, as you can imagine, you're going to be using these over and over again. Hank, what are you doing back there?
I was trying to put my, like, second lanyard back in the pocket.
All right, so I got my 45s. So the cosine and sine of 45 are root 2 over 2. Everybody okay with that? After you do a few of these, you're going to have a bunch of stuff with these numbers memorized. Now, I don't have my 30 picture drawn, so I'm going to go ahead and draw my 30. So the sine of 30 is 1/2. And the cosine of 30 is root 3 over 2. Huh. What's this answer going to look like? Is it the same thing? Now, there's 2 things going on here. One is that since these are your special triangles, aren't these angles always going to be some combination of these? So it doesn't surprise me that I'm getting 1/2s and root 3s over 2s and root 2s over 2s. That doesn't surprise me at all. That's what's going to happen on all these. But can you tell me why this answer is exactly the same as the last one?
Good.
You can't
No.
tell.
75 plus 15 is 90.
Okay, and what do we know
And
about
sine
the
is-
sine and the cosine? They are co-function identities. So the sine of an angle is equal to the cosine of its complement. So the cosine of 15 is going to be the sine of 75 because they're complementary, and that's what it means to be co-function. Sine, this is cosine. Okay? All right, we're going to do one more, and then I promise I'll shut up. One more. Let's do the tangent of 295. Now, right now, you are thinking,
They're just making fun of me.
Mrs. Ford, how in the world am I going to add 2 of my special angles together and get 295? Alana.
What we do like both between 270 and 295?
Alana is saying, in her own special way, there are a lot of 60-degree triangles. When I drew this one, I drew 60. But isn't there a 60-degree triangle in quadrant 2? And that angle is 120. And there's one down here, and that angle is 240. And there's one over here, and that angle is 300. So you don't just have 60, 30, and 45. You have all of their versions. So for 60, it's 120, 240, and 300. And don't let me pull a fast one. Do you see what I'm talking about? These angles, if I draw them, have a reference angle of 60. So they operate just like a 60. What are the 30s? 30, and then over here it would be 150, 210, and 330. And what are the 45s? If all these were 45, it'd be 45, 135, 225, and 315. Those are these angles. If you draw them, you will get a reference angle that is either 60, 30, or 45. So some combination of these might add up to 295 or subtract to 295. You see anything in there that might give you a 295? Well, a 45 has to be involved because that's the only way you're going to get a 5 on there. So, what's 330 minus 45? Is that supposed to be an 8?
Yeah, I'm getting a lot of 285.
Yeah, I think I made a misprint there. I think that's an 8. I don't think we can do 9 because that would be 35 off. And I made it be 45. All right, so now that we fixed the problem, please remember to do that. What did you come up with that gave you 285? Oh, I heard somebody say 150 and 135. How many possibilities are there? Lots. So we're just going to go with Joseph's because it's a good plan. And we're doing tangent. Okay, so that formula says tangent 150 plus tangent 135 over 1 minus tan 50, 150, tan 135. So just plugging in my alpha and beta into my tangent sum formula, because Joseph chose to write this as a sum. Okay, so now I'm going to need to draw pictures for 150 and 135. So here's 150. What's the reference angle for 150? What's this angle in other words?
30.
30. So 1, root 3, 2, and then don't forget the negatives. Because as soon as you draw an angle not in quadrant 1, you're going to have to deal with negatives. All right, what's the reference angle for 135? 45. And another negative there. All right, here we go. What's the tangent of 150? We'll plug it in. What's the tangent of 150? 1 over negative root 3. I'm going to write that as negative root 3 over 3. Plus, I'm going to put a minus because the tangent of 135 is negative 1. Same two numbers go in the denominator, only they're being multiplied in the denominator. I do not know why that's a 5. So, negative root 3 over 3 minus 1 over 1 minus root 3 over 3. These two negatives cancel, so I'm left with that minus there. Well, that's a mess. Is it a complex fraction? Yeah. So we'll multiply everything by 3. Negative root 3 minus 3 on top, negative root 3 minus 3, over 3 minus root 3 on the bottom. Those are not the same. Please don't cancel them out and say 1. You see you have an extra negative? So they don't cancel. Nothing cancels. We're going to multiply top and bottom by the conjugate. By the way, we hate the tangent formulas because they require so much arithmetic. This is all arithmetic. So on the bottom, my radical is going to cancel, and I'm going to be left with 9 minus 3, FOIL on the bottom. 9 plus 3 root 3 minus 3 root 3 minus 3. And on the top, FOIL. Negative 12 minus 6 root 3 over 6. If I combine like terms. Anything happen with that? Take the 6 out, so negative 2 minus root 3, there it is. Now, about 30 seconds of that was trigonometry, all the rest of that was just arithmetic, dealing with the fractions and the radicals. All right, so we got some homework due coming up here, so pay attention to that.
Whenever you have that,